Hi everyone! In this video I'm going to talk about the Yield v2 automated market maker, also called YieldSpace. It is very similar to the automated market maker that we had in Yield v1. It's identical in terms of math, but we have just updated it a little bit and we have made it more gas efficient. At the core, what we are doing is in this paper is where Dan Robinson and Alan Nimberg and Lev explain how to build an market maker that will be operating in interest rate space. It's a little bit like the Uniswap invariant, but that also takes time into account. So it's a slightly more complicated formula. Exactly how much more complicated it is? Well, it is quite more complicated. So is this one here. You need to have an exponential here. In Uniswap it would be x times y, it would be equal to k, which would be an invariant that would be derived from the number of share tokens, I think. I don't really remember. In YieldSpace we actually have two exponentials. And if you know a little bit about math in Solidity, having exponentials is actually a lot more complex than it sounds like. And doing exponentials with fixed point numbers, as it happens to be the case, is even harder. This k is 1 divided by the number of seconds in a number of years. For Yield v1 it was 4 years, for Yield v2 we have chosen to do 4 years. So it's a very small number. It's 0.0000, lots of zeros and then some numbers. So it's a very small decimal. And that is multiplied, and this and when you convert the formulas, what you end is elevating this k to an integer, or the other way around. I actually don't remember, but that's not really what you should worry about. What you should worry about is that we are using fixed point math and we are using exponentials, and that makes the math very complicated. Exactly how complicated does it make it? Well, it makes it very complicated. Complicated enough that Alan actually, when he contacted me the very first time, he told me that he needed someone to help him with the math, and I had written some fixed point math libraries, and I had written some articles and so on, and I saw what he was trying to do, and I knew that I was going to be completely out of my depth, and that there would be only one person in the whole world that would actually know how to do this stuff, which is Mikhail Vladimirov, with which I had been sparring for a while about fixed point math. So we reached out to him, and what he did was to license to us their math library, which instead of being a fixed point math library, which would be easy to understand, uses a 64.64 format. Here it says, which makes certain math operations a lot easier and more efficient. If you go to the repo, this math6464 library is the one that they have at ABDK, with the only difference that it has been updated to the latest version of Solidity. So you can probably make a diff between both to see what are the differences. And then the functions in this library are regular functions that are used in a few other solutions. There are not so many people that are brave enough to use this. I am not. Vladimir did it. So what Vladimir did with this math library, which you can learn about because it will be useful for you perhaps in the future, but I would expect it to be relatively solid. What we got was this YieldMath library, which we used in v1, and for v2 the only difference is that we have again upgraded the pragma, and later down I'll show you that I've rewritten the variables so that they're actually easier to understand. This library, this file actually has two libraries. It has a library to compute exponentials that are not in the original math library, and then there is a function to compute the formulas that are in the white paper. In terms of exponentials, there are only 3 functions here. There is a logarithm, base 2 logarithm, which you will see that through the middle is commented out, because in Yield v1 we decided that we only needed so much precision, and this saves us half of the gas of this function, and that's quite important. This calculates a logarithm in base 2. This calculates an exponential for x power to raise 2, so it's the square of a decimal number. Same in this one, which is a completely iterative solution. We commented out half of the function to save half of the gas, because we didn't care about the last 10 decimals. There are fractions of small fractions of another, like 10 to the power of 12 way, which we could deal with in a different way. That's what you get in exp6464 plus a generalized power function using the previous two. And then with this math function here, you get the actual YieldMath library here, which is where the formulas for the invariant for the automated market maker are implemented. There are only 4 functions: one to buy underlying, one to buy FY tokens, one to sell underlying, one to sell FY tokens. They are not exactly the same thing. It's not the same thing to sell FY tokens than to buy underlying, because in one of them you determine how much underlying you are going to spend, and the other one you determine how much FY token you are going to get, and the fees also work differently. So that's why we need 4 functions, because it depends what do you want to be sure of how much underlying you are selling, or you need to be sure how much FY token you are buying, and vice versa if you are selling and buying the other two. These functions, you can plot them to the functions in the paper with a little bit of magic trickery to move components around, and yeah, basically that's what they do. Here you will just do the formula, checking that nothing overflows, and here at the end of each one we include a term that would add a tiny fee at the end, in the like 1/1,000,000th of an ETH, which is not actually to make any kind of profit to anyone. It's just to make sure that those 64 lines that we commented out in each function that make the last decimals of each logarithm and exponential be random, we make sure that that variability would be always in favor of the protocol, so that the protocol would never lose money. But that's not a significant fee for anyone. The significant fee comes from G. So G is a parameter that appears in the white paper here, this G, which is the fee that is applied. The fee is multiplied by time. So you get higher and higher fees when you are farther from maturity, and the fees decrease as you approach maturity. How big are the fees in this behavior is determined by G. So when we calculate the formula, this will determine the fee, this multiplied by the time to maturity, and this will be the invariant that will determine, I think, the convexity of the curve, but ask Dan, don't ask me. And this is a library, so it actually doesn't interact with any contract. You supply all the numbers and you get a value out. So the automated market maker will introduce what are the token reserves initially, what is the amount to be traded, time to maturity, K, which is the parameter for the maximum time, and G, which is the parameter for the fees. And with that you say, I'm selling this much, these are the reserves, this is the time, and the library will tell you this is the other part of the trade. So you have the 4 functions here. Okay. They are all pretty similar, but they have those subtle differences that make them different. Okay. And here we don't use it, but if you're interested, there is the invariant that mentions in the white paper that will show that each pool always increases in value with each trade, meaning that the pools don't get trained out by trading, they always go up. This math library that calls the other math library that calls the other math library at the end is called by Pool.sol. Pool.sol is an automated market maker, very much in the following the design of Uniswap v2. That's what we took at as a basis. We added a few things that we found would be relevant, like adding a permit, ERC 2612 permit, so that you can use that with the tokens. We implemented the same kind of time-weighted average price, but in our case we record rate, so meaning that you can use these pools as a rate oracle, and for that you use very much the same as you get in Uniswap v2. Of course, sorry, I forgot. So in YieldSpace, each pool trades between an underlying and an FY token. If you have FY DAI at maturity, you can change it for DAI. You can redeem it for DAI, FY DAI. Then the associated pool would be FY DAI and DAI. That was in Yield v1. For v2, this would be also FY USDC, and this would be USDC. This would be FY WBTC and WBTC. You follow the drift. This is created through a factory. So we use this trickery to determine the name. And that's it. Some things can work before maturity. We can set the parameters. The owner of the pool can set the parameters for the fees and for the decay, so it can modify the curve according to conditions and governance. And the rest is here. You get the balances. This is an interesting thing. To have a higher capital efficiency, we realized that we could make an amount of the FY token reserve as virtual. Well, Dan realized. The pools always need to have more FY token than the underlying in order to trade. If those reserves would be in the other order, the rates would be negative, and that would be very bad. So, since we can guarantee, because we are going to put checks over there, that the FY token amount will always be higher than the underlying amount, we did a trick and we actually virtualize all the FY token that we are not going to use. So the FY token balance would be the actual FY token in the pool plus the total supply, plus the amount of pool tokens that we have issued. And that works out. Ask Dan, I don't know, but it works out. This is a little bit disjointed. Sorry if I'm not making much sense in the order that I follow. But anyway, there are reserves. There is TWAP, TWAR, which is the oracle. This is the function that updates the oracle. Again, check Uniswap v2 is not different. It only does it only stores a different value in here, which is the ratio of the balances. And I'm going to skip the liquidity functions to go to the trading functions. I'll leave the liquidity to the end. The trading functions are, again, not very difficult. They're a swap. Okay, so here I'm selling base. I know how much base I'm putting in. I'm obtaining a FY token. What I will do is to call sell base preview, and sell base preview, what it does is to call the library. Okay. So basically, what this function is doing here is just at the end just calling the library. So I gather all the data. I call the library to know the result of my trade, I check that the caller is getting enough tokens as he wanted, update the oracle, transfer the assets, and emit the event. And if you are a little bit keen-eyed, you will have realized that I only do one transfer. I am only giving out fyToken. That's because the user needs to have transferred before to the pool an amount of base to sell. That's why I'm not here saying how much am I selling either. The user will send underlying to the pool, and then it will say sell, and the pool will check how much more of a balance it has than it was cashed. That's the amount that is going to be sold. Calculates the trade and then sells the rest of the assets. We do it this way. Uniswap does it this way, not only because that this allows us to calculate the oracle prices, but because this allows us to chain actions. So we can have something in the vault that generates a token that leaves it directly in a pool, and then trade, and the pool leaves the result somewhere else with reduced amount of token jumps between contracts. This trade is repeated for the 4 different formulas. So you have sell base, you have buy base, which is the same in a way, with the only detail that since you are buying, you actually don't know how much you are selling. You know, okay, I want to get one die. You cannot know in advance how much FY die you are going to put, so you need to either in the same call the library to know it for sure, or you send a bunch to the pool, more than you are going to need, buy the die that you actually want, and then once you have bought, you can call one of these 2 retrieve functions to get the change. So I'm giving you 2 FY die, I'm buying 1 die, and then I go to the pool, how much is left? Oh, okay, give me the change, please. We do that just to be able to maintain the pattern that you send tokens to the pool and then swap. This is repeated for the 4 different formulas that we have to sell fyToken as well and to buy fyToken as well. They are very repetitive, but they have their differences, so we had to do them again. All this is quite similar to Yield V1, except for the detail that now there is a rate oracle, and now the pool won't pull any tokens from the user. You need to drop the tokens in the pool before and then trade in the same transaction. The part where this contract was very heavily changed from V1 is how we add liquidity, because we realized with V1 that having to provide precise amounts of each one of the tokens in the pair was very uncomfortable for our users. That's the behavior that you expect of Uniswap V2, that you have to provide this much DAI and this much Ether to be a liquidity provider. In our case, we decided that it was more convenient to just let the users provide DAI, have the pool do an internal trade, convert part of that DAI into FY DAI, and then add the liquidity so that the users could do it with just one transaction. In V1, we did this with an external contract that would do all the calculations, and it was hideously expensive. So in V2, we decided to just do an internal virtual trade. The pool can do a trade, record the numbers in memory, and then do the liquidity operation, just with the caveat that something needs to be calculated off-chain. Let's see it. So this mint internal function, it takes here a boolean, calculate from base. It takes an integer, which is how much fyToken to buy, and then it has some slippage limit in there. What does it do?
if there is any FY token to buy, what it will do is to calculate the trade internally and say, okay, so this guy has provided this much this guy has asked me to buy this much FY token. If I buy this much FY token with this base and this FY token that I have in the reserves, then he will have to sell me this much base, this much underlying. Okay, so then it knows that if this trade would happen, I would have to add this much to the FY token that he's providing, remove this much to the underlying that he needs, and also apply this to the reserves. This obviously will be calculated off-chain to provide the exact amount of FY token that needs to be bought with the desired base so that the result matches the reserves of the pool, with the result that you just provide DAI, and the pool internally will think, okay, so if you provide DAI and you tell me that you sell this much, that you want to buy this much FY token, then this will be the numbers after that virtual trade, and then this much will be the liquidity tokens that you will get. That's this math here. But there is also the thing that you might want the change to be left in underlying, or you might want the change to be left in FY token, because you will calculate it off-chain, but by the time that you execute the transaction to add liquidity, the market might have moved a little bit. So you need to provide for a certain slippage. And since you are providing for a certain slippage, if that slippage is not used completely, you will have a little bit left as change that you want to retrieve. So you can choose whether you want the change to be left in underlying or you want the change to be left in FY token. That's why you have two here. So this is if you want to use 100% of the underlying. This is if you want to use the 100% of the FY token. So once you have calculated the virtual buy, the virtual operation, if you had to do it, and you have calculated how much you are providing here to the user, then you can just check the slippage, update the oracle, mint the pool tokens, return any change if necessary, and you're done. Again, the user didn't transfer any tokens in this function, didn't take any tokens from the user because the user first sends the tokens into the pool. But the overall result of this little piece of magic is that the user sends one type of tokens, executes one transaction,
and gets pool tokens in a very cheap way. This is very complex. I think it works. I haven't managed to break it, but if something would break, it might be here. So we will fast this. Then for burning is the same. And when you burn, you would normally get FY token and underlying in the proportions of the pool, but that's not really what the liquidity providers do. In this case, it's a lot easier because we can just calculate how much the user will get when burning the liquidity tokens, and if the owner has asked to convert everything into underlying, well, we do a virtual trade and update the oracle, check a slippage as usual, and then transfer the assets. So the same, when you burn liquidity tokens, instead of getting one of each, you get the one that you really want without having to do another trade afterwards. Why not many more automated market makers implement this? I don't know, but I find it very useful. And that is the YieldSpace, the Pool.sol that we use in YieldSpace. It is more complicated than the Uniswap V2 pools. For two main reasons. Basically because it calls the YieldMath library that is more complicated than a simple multiplication, and also because we have added this feature of being able to add and remove liquidity, to add liquidity with any of the tokens in the pool, and to remove liquidity and receive only underlying. We didn't implement the remove liquidity and receive only fyToken because we didn't see the need for that. That's YieldSpace. It's very complicated in the math. It's not so complicated in the sense of pathways. This is the part of Yield v2 that is almost completely decentralized, like Uniswap. We can do that. We implemented on top of this PoolFactory, which the only thing that it does is to deploy the pools using create2 and giving the ownership to the person that deploys the pool. That ownership is only used to change the fees and the K parameter. It cannot be used to drain the pool, for example. And that's it. I hope that you were able to follow this journey through math and through the automated market maker. This is half of Yield v2, is the important half of Yield v2 in a sense that without this there wouldn't be a reason for us to exist. This is what makes us better than the competition, or so we believe. Our automated market maker is fairer for the traders that trade these financial instruments. So this is very much at the heart of Yield v2. Thank you very much for lasting this far in this video, which I know it's a difficult one. And thank you very much. See you in the next video.